Welcome to the presentation. The paper is titled as Defect Detection in Electronic Surfaces Using Template-Based Fourier Image Reconstruction. It has been authored by Du Ming Tsai and Chi Kai Huang. My name is Usman Hassan. So let us go through the contents of this presentation. So first of all, we will see the objective. Then we will review some motivational factors, what prompted the authors to come up with their method. We will go through some background knowledge that is necessary to understand the paper, and next we will see the experimental results, and finally we will have a conclusion. So the objective of this paper is to implement template matching in Fourier domain so that defects on electronic surfaces such as printed circuit board and IC dies can be detected. The paper being presented here suggests a scheme wherein the power spectrum profiles of the template image and the test image are compared to identify and locate defects in the test image. So the authors not only go to the Fourier domain, but also they compare the power spectrum of test image and a template image, and their scheme is capable of detecting subtle defects as small as 1 pixel wide in a variety of non-periodic patterns. So what is the prime motivation behind this paper? So traditionally the Fourier-based methods they rely on background pattern removal using the IFT. They focus on surfaces where some patterns are repeating periodically. So as we can see in this picture, if the time domain signal is repetitive, then the spectrum is also repetitive. In this case, the frequency components that represent the periodical background can be readily set to 0, and then the IFT gives an image that retains only the defect. Okay, but what about non-periodic patterns such as PCB? Motivation number 2. If we resort to spatial domain, then template matching technique is the go-to method, but the template matching method suffers from sensitivity to noise, illumination changes, and shift changes. Okay, so for example, we have a PCB surface here in image A, and it has some circular pads and some IC leads, and in image B we have again the same PCB surface, but this time there is a scratch, and so there is a thin scratch across IC leads, and now we have to apply template matching, but before template matching we have to do realignment. So we have these fiducial points. Using these fiducial points we first align the test image with the template image, so and then we subtract A and C. So when we subtract A and C, we obtain image D. So ideally it should contain only the scratch, but we can see that many residual patterns are also visible. So it means that the template matching in spatial domain is not very successful. So the residual patterns may be because of misalignment, as random product variation renders the alignment techniques ineffective. Okay, and so now we go through some background. As we all know that the Fourier transform is a complex quantity in general, so f is equal to r plus ji, and then the power spectrum will be represented by capital P. It is the square of the magnitude spectrum, and to display P as an intensity image, we shift it to the center of the image, capital M by 2 comma capital N by 2, and then normalize it with the magnitude of log into 1 plus mod of f. Another property of the spectrum magnitude P is that it is invariant to translation in image. If the spatial domain image undergoes some translation, it has no impact on the magnitude spectrum. And then the Fourier transform is also rotation preserving. If the spatial domain image undergoes a rotation of, let us say, 20 degrees, then the Fourier transform of that image also undergoes a rotation of 20 degrees. Finally, we have a very important property that the authors have exploited. It is that the line of orientation theta in fxy will show its corresponding frequency components in the orientation perpendicular to theta in Fourier domain. And so it can be seen via this example. So once again we have the same PCB image with our defect line. The defect line can be seen making an angle of -20 degrees with the traditional x-axis as they say in mathematics. And on the right side we have the spectrum of this image, and we can see vertical lines. These vertical lines correspond to this defect line, and we can readily see that these vertical lines are perpendicular to the defect line. Okay, so if we choose the power spectrum, then the straightforward method is to use the difference between template and test images. Let us try this. So the authors present a defect-free case as can be seen here. So we can see here a PCB surface with IC leads. There is no scratch, and at number 2 we have its Fourier spectrum, and then we obtain the difference between power spectrums of this test image and the original template image, and based on that difference we reconstruct the difference image by going back to the spatial domain. So at number 3 we can see this reconstructed image, and of course a certain threshold has to be allocated. If the difference in the power spectrums exceeds this threshold, and then that corresponding frequency component is retained, and finally IFT is applied. And so at number 4 we have set a high threshold. So we can see that okay, when the threshold is set high, the difference image gives nearly uniform intensity. Okay, so can it work in the case of scratch? Let us see. Okay, so yes, so we have here the same image, PCB image with a scratch line, and we can see that we have applied the difference between power spectrums of template and test images, and then we reconstruct the difference image in spatial domain. So we expect to see only the scratch separated, but we can see that even when the threshold is set high, the scratch cannot be separated in its entirety from the leads. So the knife method, the knife approach with even with the power spectrum will not work. We need some improvements or some modifications. Yes, so the distance from the peaks to the center gives the dominant frequency of a spatial pattern in the orthogonal direction of theta. So whenever we see a peak, we should understand that the corresponding frequency component is dominant. Okay, now we see in the proposed method. So it is based on the principle that a local defect will break the consistency of local peak locations in the spectrum profiles of the template and test image. So previously we had seen the case when there is a perfect match between the power profiles of template and test images. It means that the test image had no defect, but now the perfect match is not there. For the first 3 red peaks, here we can see that they are aligned with the blue peaks. It means that the template and test power profiles are matching as far the first 3 peaks go, but if we take a look at the next 2 red peaks, they are alone. They do not match with any peak in the of the template power profile. This means that they correspond to defects or suspicious frequency components. They could be representing local defects, and we should delete the rest of the frequency components that are associated with the normal background pattern, and just we should retain the suspicious frequency components. So this is the idea behind the proposed method. Now we go through the algorithm. What are the steps? Okay. So first we go to polar coordinates, and for this we can make a lookup table. The lookup table will help translate from Cartesian to polar coordinates online, and then which frequency components are to be retained for IFT. If they meet the following three criterion, then they are to be retained. Number one is that the power of the test image should be such that that location is a local peak. If the power is greater than both of its neighbors, then we have a local peak. Secondly, at that particular pair of r and theta, the template image should not have a peak. Okay, it should be less than the maximum of its neighbors powers. And the third criterion is that that particular point r comma theta, the ratio of powers of template and test images should be greater than a threshold C. Remember that only one of these, either suppose the maximum value in the numerator happens for the template, then the minimum value for the denominator will happen for the test image. It cannot happen that we say that either of template or test image has simultaneously maximum and minimum value. So if these three criterion are met, it means that that particular location r comma theta indicates a defect. Okay. If it indicates the defect, then we have to isolate it, and what we do is that we have a spectral matrix f sub I u comma v. If we take the inverse Fourier transform of the spectral matrix, then we should have the spatial image that contains only the defect. So how to fill this spectral matrix? Okay, so if the criteria are being met, then see if the power of template at a point is greater than the spectral power of the image, then assign the spectral value of the template at that point to the spectral matrix. Otherwise, assign the spectral value of the image, spectral value of the test image to the spectral matrix. Okay, we will see it further in a moment. Okay, so and if the selection criteria is not being met, then set that particular value to 0 in the spectral matrix, take its IFT, inverse Fourier transform of the spectral matrix, and obtain the spatial domain image. This fi hat xy now should contain only the local defect embedded in a plane background. And lastly, segment the defect using the following threshold. If the intensity value exceeds mu minus capital K into sigma, then consider it a defect, consider that particular pixel as a defect pixel and retain that. We will see K further. In the authors have selected the value K is equal to 3 because they say that normally the defects are small in size. So overall, if a pixel is 3 standard deviations away from the mean, then it is indicative of a defect, so it can be retained. Okay, and one important point once again, so why we choose the maximum of these two? Why don't we just choose the test image spectral value and assign it to this spectral matrix? The reason is that the defect can also be absence of a component, not necessarily the addition of a component. a white defect can be on a black background, a black background can be can contain a white defect, and vice versa. These white dots, they indicate the retained frequency components, and in the third row we have the reconstructed image, and in the last row we have segmented images. So when C is very low, we can see a number of white dots. So on the top of the defects, many pattern residuals will also appear. I don't know whether you can see the pattern residuals in this picture or not. For me they are visible, but they don't have much intensity here. Okay, and when C is very high, some defects are missed. Okay, finally when we apply the mu minus 3 sigma threshold, the residuals and the noise is removed, and we are left with only the scratch representation. So the authors conclude that the optimal value of C is 2.0, and for the rest of the experiments they proceeded with C is equal to 2.0 fixed. Okay, so next the authors experimented with images having undergone translations, and they applied their method, and it was quite successful, and on the defects were successfully detected. Segmentation, then these residual patterns will also be gotten rid of. However, I would like to point out that in this case the authors resorted to doing alignment first in the spatial domain. After aligning the test images with the template image, then they applied their method. Why did they had to resort to alignment? It is not clear. Okay, so number 4, if the test image contains a highly repetitive pattern as is visible here, in that case our method does not detect defect. Okay, so we can see in the image and its spectrum, and here we have again we can see the white dots. Some frequency components have been retained, but in the final reconstructed image we cannot identify the missed component. There was a missed component in the original image. It is not indicated in image D. So what is the solution? The solution is to partition the repetitive image and then apply the proposed Fourier technique to each of these partitions. So we can see here they have partitioned their original image into 9 sub images, and in the middle sub image in the top row contains the defect, as will be visible in the next slide. So yes, here is the defect, and this time when the authors applied their proposed Fourier process, they were able to successfully detect the defect. Another advantage of partitioning the image, that is it reduces the computation time. Normally the computation complexity of fast Fourier transform is image size multiplied by log of image size, but when we have sub images each of size small m by small n, then the computational load is reduced to image size multiplied by log of sub image size. So in the picture below shows how the computational time decreases as the image is partitioned. So we can see that the overall the computation time decreases from 0.58 seconds to 0.38 seconds. And as far as single sub image is concerned, as its size is reduced, first the computation time is drastically reduced, then it keeps on reducing, but the rate becomes slower. And finally, also experimented with a variety of defects under different pattern layouts, and they saw that their method was successful in detecting defects of open circuit, of short circuit and of missing components. Conclusion is that the proposed method, while using the global representation of the Fourier spectrum, can identify local spatial defects, and it is practical for automatic defect inspection where perfect alignment may not be possible. Now, there are some points which should be discussed. When the test image has undergone rotation, why does the proposed method resort to alignment? Because they claim that advantage of their method is getting rid of alignment. One of the advantages is this. Secondly, how to improve the proposed method so that we do not need to shift back and forth between polar representation and the Cartesian representation. How to do the reconstruction using the polar FT directly. This will be an extension of this paper. Thank you.